So maybe we start the day again together, turning on the cameras and saying good morning to everybody. So I said some of you were working yesterday on the code. I'm happy about that. And yeah, I'm happy about the challenge that I hopefully can donate a lot of money today. And yeah, today Patrick will join us also from the real lab, where he will present the lab room to you and how he conducts experiments. Right. Maybe we start today first with the lecture, and when Patrick is ready to conduct experiments and to demonstrate, you are ready, Patrick? Okay, if you are ready, then go.
Yeah, so I'm setting up the first experiment, but I can show the room, of course.
Yeah, go ahead.
Oh, but I have to disconnect from the local network. Let's see if I get thrown out when I connect to wirelessly. Yeah, so this is gonna be like a weird flat tour, but this is how you come in. So there are all the chairs and PCs where you could work. And then we have all the vehicles on this shelf. Yeah, there are also some bikes here with which we work. And the driving plane is right here. I don't know if you can see the vehicles at the back. Yeah, so I positioned 4 of them right now. You can see there's a TV screen on the back, so there we can also show the lab control center view of the current experiment. So you can see what's going on below on a digital screen. And we have in the lower, also in the back here, there's also a server rack where we have all the NUCs. So these are the PCs that we use for every vehicle. I don't know if you can see anything in there or just the reflection. So on the ceiling, the indoor positioning system, we mounted it on a aluminum profile, and there's the lab cam which took your experiment videos. And yeah, I guess that's about it. Do you want to see anything else?
Can you show the vehicle?
Up close?
Yeah.
Yeah. This is how a vehicle looks like from the top. So maybe let me get one hand free. So you have the Raspberry Pi, the IMU in blue, then here's the motor driver. The black thing is the connecting PCB with the LEDs. Large battery, and the motor is on the other side. Everybody happy? Okay. Yeah, if you are all right with it, Bassam, I would just leave the camera running on the driving area. So if your lecture is boring, they can. Just kidding, just kidding.
Yeah, fine.
Okay.
I think first we can watch you conducting an experiment, or should we just continue with the lecture now?
Yeah, so if it runs first try, we could do that, yeah.
we can wait and look at the vehicles. Here you see the...
I'm doing a Julia, Victoria, and Dennis experiment now. So Dennis, it's not the latest commit, right? That I should run. Okay. You have to wait for 15 to boot the last one I set up. Okay, and we're good to go. Deploy. Start. Okay, I actually ran Matthäus and Adam's experiment. That's the one I have set up. I'm looking forward to the result presentation because I think they did something completely different than the other teams. But you're not changing the speeds, are you? Matthäus and Adam?
I don't know if Adam is here. Actually, he was working until late night on this code. I don't know how is the last results. Maybe he is coming in a minute.
Yeah, very nice. Now you saw how we conduct experiments. You saw the room, and yeah, you see that the idea of the lab is to see your ideas develop into reality. And of course, due to Corona, we see the reality just on the screen, but it's still reality. Yeah, what you also see is the seamless development environment from simulations to experiments. The code developed in simulations during the night could be executed now in the morning in the lab. So thank you very much, Patrick. Maybe Matthäus and Erdem, if you want to communicate to Patrick on the latest version of the code you would like to be conducted, so you can use the chat, or Matthäus, you know the phone number of Patrick, so you will find a way. And now I would like to share my screen. It's working, right? So moving some windows around. Yeah, and we can start our last lecture. So in this lecture, we decoupled, to use now the words of the course, right? We decoupled from the course on, or from the lecture on control engineering and optimization. And now I'm going to introduce an optimization method to you. So we stopped before that, yeah, speaking about the model predictive control. Yeah, for now, Here again, it's similar to the network thinking. I will try to transfer this optimization thinking to you. One of the ideas. It's really simple idea, but you have to get into this thinking. Yeah, for this you can read these pages in this literature. So the idea behind sequential convex programming is, but maybe first it solves here is not really solved because we are speaking about non-convex optimization problems. And non-convex optimization problems are, in the terms of computer science, NP problems. And yeah, the maybe 1 minute version explanation of this is that in computer science we have in general classes of problems, and the classes depend on the computation time, how fast we can compute. And in general we distinguish between problems we can solve in polynomial time. That means the time for computation of these problems we can express as a polynomial. And the other class of problems which we cannot express as a polynomial. Of course, I'm speaking about the computation time. It may be exponential, the computation time, right? And for such problems in computer science, we cannot prove if we get a solution that this solution is correct or is optimal. We can prove that it's correct by checking the correctness, but we cannot prove that it is optimal. And we cannot also guarantee that we can find a solution. So no algorithms exist for any such problems, NP problems, where we can guarantee, give me the problem, I run the algorithm, and I will find a solution. We cannot guarantee this. This is a class of problems. And non-convex optimization problems, yeah, it's maybe not 100% proven, but people argue that they belong to the NP class. So that's why here is solve and not solve. So we have to distinguish here between we find a solution and we solve and find the solution. So you may pay attention to this. So the idea behind sequential convex programming is look at the optimization problem, convexify non-convex parts of the objective function and constraints using convex approximations, and of course, preserve their convex parts, right? Maybe as you used to in control, in many cases, if we have non-linear dynamics, we linearize usually, and then we try to find the right controller and maybe transfer this controller from the linear world to the non-linear world and so on. Why we do that in control? Maybe one of you wants to answer this question. Why we
yeah, because we have developed a lot of approaches for linear models. So we want to investigate these theories and these approaches. I mean, like stability, like many other theories to nonlinear systems.
Yeah, it's right. It's just because we understand linear systems better. We have good math since years for describing linear systems, and it is similar for convex and non-convex optimization. Since maybe 20, 30 years, we have developed good algorithms for convex optimization. And we can use them to get solutions of non-convex optimizations by convexifying non-convex parts of the optimization problem. So after doing that, we solve the convex problem, and we know in optimization that we always get the global solution of a convex problem. So if you give me a convex problem, I can guarantee that you will get the global solution, right? And this is, of course, good news. Convex problems are computationally efficient. So we can guarantee that we get a solution, and we can also guarantee that the computational effort is limited. So the computational effort in convex optimizations depends also on the accuracy we want to reach, but we can guarantee that we find a solution at the solution at the end, right? Up to a numerical accuracy. So this is also why, similar to control, linear control is, of course, understandable and well understood and nice to deal with, nice to teach, but there is not a big room there for research. Why? Because it's well studied, well known. Of course, there are still some, let's say, areas where we can improve things and study things in linear control, but it's well studied. So you will not find a lot of groups developing methods for linear control. Nowadays, it's more about non-linear control. And also, of course, network systems. And it is similar for convex and non-convex optimizations. If you develop a new algorithm for convex optimization, it's nice, but it is not the, let's say, rocket science. So you cannot do a lot of research on this. It's more, let's say, yeah, maybe you can write it for as an exercise. So, but for non-convex optimizations, because we don't have the solution, we have many solutions, you can argue that you can get better solution for a certain problem, and people will believe you that you are working on improving the solution of a certain problem. So what we now do, we get the solution of the convex problem. We do a new approximation around the optimal solution, and we repeat until convergence. So, and this we repeat until convergence is important in real-time systems to try to get a solution in few iterations. Well, and here we look in general at optimization problems of of MPC to see where SCP is located in our work. So here at the top level, we have optimization problem of MPC. The optimization problem, as you experienced also in your implementation, we can divide into objective function and constraints. Objective functions could be convex or non-convex, and constraints could be also convex and non-convex. In case of objective functions in MPC, they are mostly convex because in most cases we use quadratic cost functions, but you may also use linear program. So, and here we have the other possibility to use quadratic program. So in case of convex constraints, I'm not going to speak about it because it's well studied, well known. In case of non-convex problems, we can formulate the constraints as quadratic constraints or as mixed integer constraints. Yeah, this is what we study in our group. Maybe there are further methods or further classifications, but this is our focus. So if you take mixed integer and QB, you get mixed integer quadratic programming, and if you take LB and MI, you get mixed integer linear programming. And if you combine here again quadratic constraints with a quadratic program, you get a non-convex QC/QB, quadratic constraint, quadratic program, right? So I'm here again at this level, I am combining the objective function and constraints. So here I divided the optimization problem into objective function and constraints, and here I'm putting them again together. So how we can solve, maybe first the case we are not going to study, mixed integer quadratic programming. There are algorithms to get solutions, maybe efficient, but again, it's still non-convex. And if you want to get a faster solution, maybe you consider a linear approximation. In case of non-convex QC/QB, in general, there are two, let's say, methods. One method is the relaxation. In both cases, we have convexification, and the other method is restriction. So in case of relaxation, we studied semi-definite programming relaxation in our group, but I'm not going to speak about it, but I'm going to show you how we can use it. And yeah, we have here the sequential convex programming on the other side. Of course, you could also use the idea of sequential convex programming not only by a restriction, but also by relaxation. But the example I'm going to show you here in this lecture is about convex restriction, but also you can relax. The main idea is to find a convex approximation, and you can restrict or relax and iterate till convergence. So maybe here an illustrative sketch of the different optimization problems. Yeah, here we have a non-convex set, right? The black one is non-convex. So to get a convex approximation of this, there are two possibilities. One is to relax, means to have a greater set than the non-convex set, which is convex. The other way is to find a set inside the non-convex set, which is also convex. The one side we call relaxation. As you can imagine, we relax the optimization problem. The other way is restriction, where we tight the optimization problem. Right. May I say some words about relaxation and restriction? In case of relaxation, you increase the possibility to find a solution. And you may also find a solution, but you cannot, if you find a solution of a relaxed program, you cannot say if this solution is also feasible. Because a solution in the relaxed set could be here, and it's outside the non-convex set. So we cannot tell that this is a feasible solution. But the solution could be also inside the non-convex set. And in this case, I would argue that it is then the optimal solution if it is inside the non-convex set. But you cannot guarantee this. So in case of restriction, you cannot, of course, guarantee finding a solution at all because the set is reduced. But if you find a solution in the restriction, you can guarantee that this solution is a feasible solution because it is inside the non-convex set, right? But the condition is to find a solution first, and we cannot guarantee finding a solution. And we cannot say anything about the optimality of this solution because the optimal solution could be outside the restricted set, right? This is just an illustration of non-convexity, convexity, and relaxation and restriction. We may now look at the concrete problem of QC/QP, and now we look at the application of this algorithm of SCP to solve a non-convex QC/QP. So you may have another non-convex problem, and you could also apply this idea there, but we are here looking at non-convex QC/QP.
Sorry to interrupt you. Can you just tell me how to know that it's non-convex, or I mean the definition of convexity? How do we know that it is convex or non-convex?
Well, a simple definition of convex sets is that if you take arbitrary points in the set and you connect them, then the connection is inside the set. So this means we take these 2 points, we connect them, we see here that the connection is not always inside the set, and we say this set is non-convex.
Okay.
Yeah. Of course, this is the mathematical definition given in words. You find the mathematical definition also in the literature.
Okay.
I gave you. Right, what is a QC/QP? We have a quadratic program, right? The objective function is quadratic, and this is common in MPC, right? That we use a quadratic cost function. So that's why I'm looking here at QC/QPs. And QC/QP is subject to a quadratic constraint, right? And quadratic constraint, why I am looking here also again at quadratic constraints? Because you can use the quadratic constraint also to express a linear constraint by setting pi to 0, right? Or you can use the quadratic constraint to have equality constraints by using the inequalities in both directions. So this is the generality of QCQP, and that's why I am looking here at QCQP. So in general, PI is symmetric, but not positive semi-definite. And this means that the optimization or the constraint is non-convex, and that means that the optimization problem is non-convex, right? So in the vehicle example, the collision avoidance constraints are concave functions. Maybe I can illustrate this. So here we have a vehicle driving from west to east, and here we have an obstacle on its way. And this, the optimization problem of this vehicle following its line and at the same time avoiding the collision with the obstacle is non-convex. You can see you take a solution in the feasible set, a solution, other solution in the feasible set. We take another color. And you connect them, and the connection is not in the feasible set. So according to our definition of non-convexity, this is a non-convex optimization problem. And we could approximate the obstacle by a quadratic function, right? And I am saying quadratic function because it is in general quadratic, and maybe my drawing you experienced on Wednesday is not the best, but imagine this is an ellipse, right? So in general, a quadratic approximation of a polygon is an ellipse. Maybe for Joseph, this is common in underwater vehicles to model obstacles as ellipses. Right. It could be a circle, but it could be also an ellipse. So in general, it is a quadratic function, right? And why people use rather ellipses than circles in underwater modeling? Because using ellipses, you are more accurate, right? You can the loss of feasible set is less. So I may give here an example. If you want to cover this polygon by a circle, then the circle maybe looks like this. And this means that we lose this set, which is feasible. And if we choose to model it as an ellipse, then maybe we can find an ellipse like this. Okay. Imagine this is an ellipse, right? Okay. For your information, there is a problem using ellipses if you rotate them, because then you don't get a QCQB anymore. Maybe you have to do some more approximations, but this is just a hint. So let us look just at circles for simplicity now. So this is again the algorithm in words. but we are engineers and want to see algorithms like a side of code, right? So the algorithm says I can solve, and solve is not finding the solution, but a solution, the non-convex QC/QP. So the input is the non-convex QC/QP. The output is a solution vector of the non-convex QC/QP. Okay, in the first step, we initialize our iterations with C equals 1. Then we determine a starting point, XC. This is in general in non-convex optimizations. You need to find an initial solution, a starting point. And this starting point is going to decide about the quality of the solution at the end of the day. Because you can, from the starting solution, just run to a local optimum. We say also sub-optimum, right? Well, number 3 is compute the objective value of the non-convex program, GC, using XC. So we take just our starting point, we put it in the non-convex optimization problem, in the objective function, right? Not in the constraints, in the objective function. Because constraints we have just to check if they are, if our solution satisfies them or not. Well, we compute the objective value using XC, and we are still here in the non-convex program. And number 4 is form a convex approximation of the non-convex parts of the inequality constraints using XC. Right? In case of linearization, which we are going to use also here for simplicity, is linearize the quadratic non-convex function. So number 5, compute the optimal solution XC plus 1 of the resulting convex program. So you have to pay attention here the whole time about which program I'm going to speak, right? So here we run our optimization algorithm, something like gradient descent, right? Or the Newton method. So in step number 6, compute the objective value of the non-convex program JC plus 1 using XC plus 1, right? So till now we have a starting point XC. We use XC to find a convex approximation. We solved the convex approximation. We took the solution and we computed the objective value of the non-convex program using the solution of the convex program. Right. Now we check for our progress. So we check GC minus GC plus 1, because we are speaking here about minimization problems, right? And the objective function should decrease. Well, we compute it JC minus GC plus 1, and it is, if it is inside some epsilon, then or below than some epsilon, we return XC plus 1 as a solution. And in the program, else we increase the iteration counter and go again to 4. So here we initialized our algorithm, and he is the main body of our algorithm. Right, I'm now going to explain the steps one by one. So first, look at the starting point. So we are dealing with MPC, so we can use the time-shifted solution from the previous time step of MPC, similar to the idea of networked MPC, where we communicate plans, but the plans may be outdated. We have to delete outdated parts of the plan and add new values to the plan. Right? May I write it here? Maybe just like a window. So assume this is the solution from the last time step. This is the solution at t-1. And now we have the time t, and at t, we delete just the first solution, the first value in our solution vector, and add 1 at the end of it, and then we have a shifted solution. So because in MPC we repeat our computations again and again and again, this may be a good idea to shift the solution and use it as a starting point, right? So if we don't get a feasible solution, which we cannot guarantee, maybe we have a bad local minimum. That means we have a bad starting point, and a solution to this is to try other starting points. So this is all about the starting point. And now let us look at the affine function. I don't know what's wrong here with the figure, but I'll fix it. So it's slide 27. Right. So affine function. Something is wrong here. Here we should see the algorithm. So, but assume we are speaking here in the algorithm about the convex approximation. So the convex approximation is a local approximation, of course. And in case of the quadratic constraints, we can use a linearization of the quadratic constraints around xc. And we will now look at some properties of this approximation. So it is the best convex approximation of a concave function. It's a affine approximation, right? A concave function is something like this, right? And the best convex approximation of a concave function is its affine approximation, which means, with other words, the linearization, it's something like this. And this is proven in this literature. So a affine function lies above the concave function at all points. That means the affine function is globally upper bound on the concave function. So you can see it directly here and imagine it. Take any line above the concave function, and all points of the concave function lie below the affine approximation or the affine function. And the resulting program is a restriction of the original one. Of course, this is a restriction, right? You can maybe see it directly here. So we using this affine function, we restrict our solution. We restrict its, let's say, a higher restriction of the concave function. So now we have the algorithm again, and in this step, we compute the optimal solution xc+1 of the resulting convex program. So solve convex subproblem, it's fast, we know, because it's convex. And iterating around the new solution produces solutions with lower objective values because we are dealing with convex functions here, and therefore of original problem. Maybe I'll explain this in some words. So we have a solution. We approximate our non-convex program again around this solution, and we solve again. And we can just get better solutions because we are dealing with convex programs, right? In convex optimization, we can just from iteration to iteration get better. And because we are dealing here with a restriction, if we improve in our convex approximation, we improve also in our non-convex program. Right, and here some words about the progress evaluation. So we compare the values of the objective function, and if the objective function doesn't decrease a lot, we stop. So decreases in objective value of original problem indicates progress. So we use just the original problem to evaluate our progress. And now we get to some discussions about the SCP algorithm. So it is fast. So we tried in our applications, we get solutions in less than 100 milliseconds, but it depends also on the scenario. So we get locally optimal solutions of QC-QP problems. So SCP subproblem is a restriction of QC-QP. SCP is, if SCP is feasible, implies QC-QP is feasible, right? If we deal with feasibility issues, then our restriction is too restrictive. And I'll tell you in a minute in using an example how to deal with too restrictivity, if I may say it like this. So solution is to use a slack variable. And I'm going to demonstrate this using an example. So in our example, we have an objective function to follow a predefined reference trajectory, like you know it now from the lab implementation. And yeah, the goal is to minimize the distances between the vehicle position and the reference trajectory. And for the control input, only accept small control changes, control input changes, and which means keep the steering angle changes as small as possible. So we have here prediction horizon and control horizon. So now looking at the constraints, we have input constraints: do not exceed a maximum steering angle, do not exceed a maximum change of the steering angle per time step, and do not exceed a maximum lateral acceleration. So you can translate these constraints to the problem you have already implemented in the lab. So you constrain the velocity, for example. And we have a collision avoidance constraint, or constraints in general. And they say do not collide with other vehicles and obstacles. And this constraint is non-convex. And we have to deal with this non-convexity.
Sorry to interrupt, but for the modeling of this constraint, do you just use like a constraint on the output to say, okay, the output position of the other vehicle is not allowed for me to move on? Or how is it mathematically modeled?
We will get to it in
oh, sorry.
in the next slide, actually. So it just says that the distance between the vehicle and the obstacle and between vehicles should be greater or equal to a safety distance. And this distance should count for the geometry of the vehicles and also for the sample time. And maybe you add also a safety margin. So, but here in our example, we will look at a simple example. It's the most simple example of collision avoidance you can see. We have a vehicle driving with a constant velocity towards an obstacle. This is the obstacle, and the obstacle is a circle. And the task of the vehicle is to follow its reference trajectory and at the same time avoid the obstacle, right? And in our study here, for the constraints, we are just looking at the last point in the prediction of the vehicle, right? So if you formulate this problem, this optimization problem, you formulate it like you check every point in the prediction horizon for the safety distance to the obstacle. And here we are looking at the first time the prediction of the vehicle hits the obstacle. Right. And what we do, we have a convex approximation. Which color should I take? Maybe green, right? Yeah, we find an approximation of the quadratic constraint, which is here simply a circle, and we saw that the best convex approximation is the linearization. So we linearize it and get this line as a constraint, which he says that this here is outside the feasible set. With other words, it says that this point should be moved to this area, to the feasible set. Yeah, and this is the first iteration. The point is still in the infeasible set. I don't know if I'm going to explain it, but let us go through the iterations. So in the second iteration, it is still in the infeasible set. And actually, we allow it to stay in the infeasible set using a slack variable. But we check the slack variable. The slack variable is just used for getting to a solution. But you have to check that the solution, in the solution, the slack variable should be 0 at the end of the day, right? It is just like a help variable, the slack variable. It helps us to get a solution, which is actually not a solution, but using the slack variable, it's a solution. And we can improve using the slack variable from step to step, and at some step we get a slack variable equals 0, which you will see in the next iterations. So at iteration number 3, something happens. So at the first 2 iterations, you didn't see any improvement, any movement of the predictions. They were very small, and now at iteration 3, we have a larger movement of the predicted trajectory. And at step 4, it is the first step where we get a feasible solution according to the non-convex program, but not according to the approximation. And now you see that it is a restriction, right? If you look here at this point, the red point is slightly behind the line, which means that for the approximation, this is not a solution. This is just possible because of using the slack variable. But according to the non-convex program, as you can see, the point is outside the circle, outside the obstacle, and yeah, it is a solution. And you see, okay, it is not the best solution, but it is a solution. So if you want to save computation time, you can stop at this point and use this solution, because we are using MPC and we are using predictions, and depending on the length of the prediction, you can accept this solution, and at the next time step you could try to improve, because you see the change of the vehicle position is not big at the first steps, and the vehicle will move and we will compute again and again. So for MPC, it would be fine to stop now, but we don't stop. We continue to iteration number 5, where we get a better solution, and it is the first iteration where we get a solution according to the approximation, which is more restrictive than the non-convex set, and of course, according to the non-convex set. So this solution, as you see, is better than in iteration number 4, and we can continue improving in number 6, 7, 8. So we get better and better solutions, and according to our condition, we stop at iteration number 8. And now let us look at some analysis of this example. So we note the convergence of SCP. Actually, this is the objective value of SCP with this hat, right? And as introduced, JC is that of the objective function of the non-convex problem. The value of the approximation can be understood as a convergence of SCP, and the value of the original problem can be understood as a progress of SCP, just an interpretation, right? If the objective value of the non-convex program improves or moves in general, how can we interpret this? We interpret it as a progress, right? We are progressing towards the solution or a solution. The improvement in the objective value of the convex approximation, we can interpret as a convergence we are converging towards the or a solution. So here you see a summary of the 8 steps. And on the right, we see the values of GC hat and of GC, and additionally of SDPR, which is semi-definite programming relaxation. In a minute, I'm going to speak about it. So here we see the value of the original problem, and we take that what we get from our approximation. We take the solution of the convex approximation and put in the non-convex program, and we get some values of some values of the objective function of the non-convex program. So at the first iteration, you see it is 10 to the power of minus 15, which means this point is still very near to the reference. And it moves, which you see here, because from step to step till step 4, this point is moving away from the reference trajectory. And at this point, we get the worst value of the objective function of the non-convex program. It just evaluates the distance between the solution and the reference trajectory, right? And if we look at the restriction, we start here because of the slack variable. So in the first iteration, we have a larger value of the objective function of the convex approximation, right? Because of the slack variable, right? In the second iteration, we have also a high value, and you see that the value is decreasing from step to step. Why? Because the value of the slack variable is getting lower and lower and lower. So at step 4, the value of the slack variable is still some value, not 0. But at step 5, it is 0. And you see, we can interpret that we use the iterations from 1 to 3 to get to a solution of the non-convex program. Because it is a restriction, we use step 4 to get to a solution, or to get to the solution of the convex approximation. And starting from 5, we just improve. It is just moving towards a better solution. So theoretically, you could stop after 3. I would suggest it is better to stop after 4. And if you want to get better solutions, you can continue improving. So here we see 10 iterations because we had, so in reality, we continued here improvements, but the improvements you will not see visually here because they are really small.
Can I ask something?
Please.
So if you want to implement this in real time, do you limit the number of iterations? And do you stop the iterations when the difference between the current and the previous solution falls below some threshold?
Yeah, this is a possibility, right? To say, okay, in real time, I can just run 5 iterations, for example. And you can say, okay, after 5 iterations, if I don't get a solution, I have to stop. I have to go to a fallback solution. And what you said is also correct and good. This is really a good idea to say okay, I'm not getting to a solution, but my solution doesn't improve. That means I am in really a bad, I stick to a really bad minimum, which is not feasible. And it is better in this case to stop. But as you see, the improvements at the first iterations were very small. So you cannot here, starting from the first iterations, say that you should now stop after 2 iterations because the improvement is not really good. So this depends on the application and implementation. After how many steps you could say that there is no improvement, and that means we are not going to get a solution. Actually, in this case, it has something also with numeric issues, because we started here at a steering angle of 0, right? And maybe you could imagine it to we have to put some effort in the first iterations just to move the vehicle in one of the directions to get some let's say disturbances on the steering angle. So the starting point in this example is not really good. But we cannot, maybe you can do better in this example, but you do worse in other examples. If you try to improve something in non-convex optimization, then you improve things for one example and make them worse in other examples. This is why it is interesting. Well, let us look here at the interpretation of the decrease. So the change of the objective value of the approximation can be interpreted as a predicted decrease of the objective value, because it's not the real decrease of the objective value, right? And dj can be interpreted as, or it is actually the real decrease of the objective value. And our prediction is always below our improvement or our decrease, because it's a restriction. So again, in this example, the first, or you see here, maybe, okay, here is the hub. So maybe I write it here, DJ hub, right? So it is the blue one. And we see that it is below that of DJ because it's a restriction. So now we look at the control input, and now you will see what is happening at step 4, right? So in the first, okay, maybe first we choose HU to be 3 here in this example, right? And here we see the different values of delta U. So again, U is the steering angle and delta U is the change of the steering angle. And we see the values in red at for the first prediction point, t+1 is the next, t+2 is the next. So HU is 3, right? That means we change the vehicle is allowed to change the steering angle at the first 3 prediction points. So here we see that all are very near to 0. So the vehicle or the prediction doesn't move. At the second one is also the same. At the third, we have a small movement. And at the fourth, where we get the first feasible solution, delta ut means the first one in the prediction takes the effort to get to a feasible solution. So which means here we change the steering angle just at the first point, right? You can imagine it's this solution, just an interpretation now, it is similar to HU is 1. And now we can improve, we can get it down, and the other 2 steering angles increase, and we get the first feasible solution in the sense of the approximation, and this continues to improve till the improvements are small. And you see here that the change at t is smaller than the change at t plus 1, and it's smaller than the change at t plus 2, which actually is good news. It's good for MPC, because we are looking in the prediction horizon to avoid an obstacle, right? This obstacle may also move. If I take the task of avoidance and put it all in the first prediction point, then I would move a lot in the first step, and then something changes, and I have to react to it, and I have to change a lot, and this means a lot of changes in the real movement of the vehicle. So the movement would be more jerky in this case. So, but here I say, well, I have to react, but in the first step, I react a little, and in the next step, I will react more, and the next step, more. Maybe you experienced this during the week. So some people are deadline people, they work for deadlines, and they submit their solutions just before the deadline, and this is totally fine, and it is also a possibility to deal with deadlines, but it's just a side remark, right? And now we look at the value of the slack variable. So we used the slack variable in the first 3 steps to get a solution. Of course, also in the 4th step, but you see the decrease of the slack variable between the 3rd and 4th step. In sense, or in for the non-convex problem, the 4th step is feasible, but it is still not feasible for the approximation. And starting from the 5th step, the value of the slack variable is 0, and this is what can be interpreted as improvement. Here somebody.
Sorry, I wanted to ask you, about the previous slide of you. This one. Here, as I saw in the books, from the receding horizon principle, they generally, I mean, we choose the first input of our control horizon is injected to the system.
Yeah.
And I saw that they explained why, because the remaining elements of our vector, control vector, tends to 0. It's that's why it's like they are neglected and they have less effect. And if we will consider all of them, they will only add more complexity, computational complexity. But as I see here, I see that the values of the steering angle are much more bigger in at t+1 and t+2 than at instant t. I don't know if the explanation of this is due to the constraints, the obstacle avoidance constraints, or maybe I understood the principle of control horizon in the wrong way. I mean, for me, it's always less.
Yeah. I may didn't explain this maybe very well in the MPC lecture. We repeat the computations at every time step, and that's why we throw from t+1 onwards away, because we repeat the computations. This is the reason why we just apply the first one, right?
It means in the second iteration we would have, I mean, how to say it, almost the same values that was found before. I mean, the second and third element, they will be the first in the second iteration, not the same, but almost, I mean, or
okay, at time t we have delta ut, right? Maybe I use this space here. We have delta ut, we have delta u t+1, delta u t+2. Of course, these are the optimal values, right? And this is at time t, right? From delta u star at time t, we compute u and we apply u at this time step. And the remaining, we discard. We go forward in our digital control and compute here. Now here is t. We compute delta u t, delta u t+1 again. And delta u t+2, right? And now we are at this point and compute a new delta u t. So, and again here we apply just u at this point and discard these values. And you may ask, are these values equal?
Yeah.
Yeah, we usually not, but we don't know. They may. Depends in first line on the changes in the environment. Means also disturbances and changes of positions of obstacles in our example, of changes of other vehicles we have to consider, changes of route conditions. So many things can influence this. And this is the basic idea of control in general, that we repeat our computations at each sample time.
My question is, if okay, if we know that when we are in like a dynamic environment that changes its state in each time step, why should we use a control horizon? I mean, why don't we should why don't we use a control horizon of 1, since we are only I don't see the effect of choosing I mean a big not a big, but for example a control horizon of 3 if we are only interested in the first one. I mean, what is the effect of the other elements on our solution?
Yeah, this is really a good question. It is a basic question in MPC. Yeah, most of people, especially if they get the first time into MPC, they ask, okay, why I should take the effort and compute things which I don't use, right? But this is the idea of MPC, these predictions. So this is, I may explain it in words, but of course you have to transfer the words to math, maybe in the textbooks. So this combination of horizon and repeating of computations can be interpreted as control, as feedback control, plus feed-forward control. So in the plan, if you go to the basics of control engineering, you know there is feed-forward and feedback, and you can improve your feedback by feed-forward, right? And feed-forward, actually, you can say what also in classical control, if you look at it, it's nothing else than a plan, right? And yeah, the repetition of computations is the control part. So planning and control, you can look at it, feed forward and feedback. So this is really a good question.
Thank you for the answer.
Welcome. We were about to look at the computation times. Just a comparison in our example between mixed integer and SCP. So mixed integer, maybe a word about it. If we get, okay, there is an algorithm solving mixed integer programs. The name is branch and bound. If we apply branch and bound, and if branch and bound finds a solution, then it is the solution. It is the global optimal solution. But if it finds a solution, and of course, the problems are still non-convex, means we cannot guarantee finding a solution. And again, maybe you now all know it also from Corona, the exponential growth. So for maybe small number of or small size of the problem, of the non-convex problem, you can solve it. But at some size, you get to the exponential part, and the computation time gets infeasible. Well, this is a very nice topic, but let me first introduce the notation here. So we have the median of mixed integer quadratic programming, median of mixed integer linear programming, median of SCP, and the maximum values of these. So we see here the maximum of mixed integer quadratic programming, and again the axis, the y-axis is logarithmic, right? And you see here the growth of the computation time. This is of mixed integer linear programming. You see you can improve using linear approximation, but not a lot. And here we see the maximum of SCP. So we see that we get better solutions. I forgot to mention the x-axis. We consider collision avoidance between agents. As I remember in the circle example. So we have 2, 3, 4, 5, 6 agents. Now we look at the median values, and the median of mixed integer linear programming is above that of mixed integer quadratic programming, and the one of SCP is below of others. And this is the main message of our lecture today is SCP, if we find a solution, then it is efficient, right? Also in maximum. So let us look at some examples, some simulations and maybe experiments. And first I would like to look at the video of Frogger simulation. So Frogger, you may know the game, Frogger. So if you don't know it, so don't worry. Yeah, Frogger started also in my generation in the 90s. We could play it also on the TV. So using the remote control of the TV. So in Frogger, you have to move an object and avoid moving objects, right? And I may repeat this video again to show you maybe first the setting. So here we have, we call this, we did it just for fun, right? So the scenario is called Frogger. The optimizer is SCP. The strategy is centralized MPC, but it doesn't matter here because we have just one agent. Here we see the number of steps and the time. On the left, we see the predicted steering angles, right? And here we see the limits between -3 and +3. This is in degree, I think. Right, and here we see obstacles in black moving from south to north with a constant velocity. And our vehicle is moving, predicting, and working on finding a solution to follow the reference and at the same time to avoid the obstacles. So the next example I would like to show you is video of experimental results. I think this is the one, right? And here the setting is, you will see the model vehicle on the right, moving from east to west. And here the boxes in the middle are our obstacle, and we use here SCP, and you will see how the vehicle follows the reference trajectory, which is the lane on which it is right now, and at the same time avoid the obstacle. I may repeat it because it's very short. And we are here a little bit faster than in the examples of multi-vehicles, because here not a lot of things can go wrong. And if the vehicle crashes to the boxes, there is no problem. They are just empty boxes. Not really empty because put some weights inside to fix them on the parking roof here. And yeah, it's a little bit dangerous because on the other side, the vehicle could hit the last obstacle. the how to say it, yeah, the margin of the parking roof, and in worst case we have an accident, but we stopped at the right point, right? And the next video I want to show you, I wanted to prove to myself that I can trust my algorithms, but not a lot. So I used an expensive car as an obstacle. As you see in the scene, it was at the end of the day, and I finished the experiments. I wanted just to have some fun, and yeah, I reduced the reference speed of the model vehicle. I enlarged the area of the expensive vehicle here, which is acting as obstacle. And yeah, my student assistant was looking the whole time that nothing can go wrong. So he had a remote control to stop the model vehicle, just to be sure that everything is working fine. Here you see in the bottom, you see the student assistant, and you see that we trusted our algorithms to avoid the expensive car, but of course with some cautions. Right. The next example is the racing one. Maybe this is the first. Yeah, we can look at it. So here we have a racing truck. It's actually, I think, the Hockenheimring in Germany, a Formula One thing. And the vehicle, the task of the vehicle is to be as fast as possible. And we used SCP to find the optimal solution. So the optimal driving line.
What is the prediction horizon here? And control horizon as well.
Oh, I actually don't remember the values. Maybe I can look up in the break. We have published a paper of this, and I may find the values in the paper. So I take a note. Yeah, and here you see it using a simulation of vehicle dynamics, the same again, but using vehicle dynamics simulation. It is very accurate vehicle dynamics simulation from the company IPG, and the name of the simulation software is CarMaker. So I found it good, good to work with this software package, because
even as we work with it in our laboratory.
You work also with CarMaker?
Yeah, with CarMaker,
yeah. It has easy to use MATLAB integration.
Yeah, especially for that, yeah. We can plug it with our Simulink models and run the simulation easily.
Yeah, nice. Okay, now we get to a conclusion. SCP, the conclusion is very easy, but just a reminder, SCP finds a good, we don't know how good, upper bound on the non-convex optimization problem, starting from the time-shifted last solution of MPC in this example. And if you want to play with the code and see my SCP code, and maybe Manuel asked for the how to implement a Slack variable.
Yeah.
You can find the code. So you may just order Cplex for academic purposes, and you can run the code and see the implementation.
Okay, thank you.
Welcome. So that's all about the lectures. Now is 10:40. Maybe we ask Patrick about the experiments. Are they done?
Yes, all done. All worked well. Worked like a charm.
Okay, and the results are in the share out folder.
Share in folder.
Share in, okay. Well, you have now your results. I would say you can now work on your presentations. So just go to your breakout sessions. Of course, take a small break, work on your presentations, and we will visit you in the breakout sessions, and we will get you together when the presentations are ready.